Cancer is a ravenous monster that eats life away from the inside. Its appetite never stops, not until it has swallowed every last trace of life. In the 17th century, some doctors even laid raw meat on top of tumors, desperately hoping cancer would eat the meat instead of the patient. Where does this endless hunger come from? In the 1920s, German physiologist Otto Warburg was studying how cancer cells obtain energy, and he discovered something astonishing. Unlike normal cells that steadily consume oxygen, cancer cells hardly used oxygen and relied on glucose at an abnormally high rate. Puzzled, Warburg added even more glucose. The result was shocking. When glucose was abundant, the cancer cells virtually shut down oxygen use and devoured glucose alone at a blistering pace. The real question was how all that absorbed glucose was being used. A normal cell can make around 30 molecules of ATP from a single molecule of glucose, but a cancer cell makes only about 2. The rest is simply dumped as waste in the form of lactic acid. Cancer cells release more than 70 times as much lactic acid as normal cells. Warburg realized that this bizarre inefficiency, that a cell would throw away efficiency just to devour fuel faster, was the fundamental nature of cancer. This discovery became known as the Warburg effect, and today we use this very phenomenon to directly identify cancer cells. When we inject radioactive glucose, the tissues that burn it fastest light up on a PET scan. Those glowing spots are exactly where the cancer is. People who learned of cancer's devilish appetite began to wonder, could we starve cancer to death? A wave of diets followed, cutting glucose, ditching carbs, avoiding sugar, all in an effort to starve the tumor. But the problem wasn't that simple. Horrifically, cancer is a living thing that can summon its own nutrients, its own blood supply. When deprived of nutrients, a tumor releases signals such as vascular endothelial growth factor. Then, new blood vessels begin to sprout around it, often by invading and destroying nearby tissue. In the end, it was the patient who wasted away. The cancer did not. So is there truly no way to starve cancer? In the early 2000s, scientists noticed something odd while analyzing PET scans. In some adults, areas near the neck and along the spine lit up with intense glucose uptake, almost as if they were on fire. It wasn't muscle and it wasn't cancer. It turned out to be brown fat, also called brown adipose tissue. The human body has two kinds of fat: white fat, which stores energy, and brown fat, which burns energy to generate heat. Brown fat is abundant in newborns, who struggle to maintain their own body temperature, but it was long thought to disappear in adults. But it turns out adults have brown fat too, and in the cold, it rapidly burns fuel to keep the body warm. In 2021, a team at Sweden's Karolinska Institutet used mice to examine how brown fat affects cancer. The results were striking. The more active the brown fat, the more sharply cancer cells' glucose uptake dropped. Over roughly 3 weeks, tumor growth fell by more than 80%, and the mice's survival more than doubled. Even more surprising, the same effect was observed in humans. In a case involving a patient with Hodgkin lymphoma, activating brown fat likewise reduced the tumor's glucose consumption. Although it was a single patient case, it was the first direct indication that we might be able to starve cancer by harnessing brown fat. But there was a critical limitation. Brown fat becomes active only at low temperatures, around 16 degrees Celsius or below. We can't keep a patient in the cold all the time. So scientists wondered, what if we could create a kind of fat that works regardless of temperature? In February 2025, a team at the University of California, San Francisco, published a study in Nature Biotechnology. They made ordinary white fat cells behave like brown fat. Using CRISPR activation, they forcibly switched on the key thermogenic regulators, UCP1, PGC1 alpha, and PRDM16. The result was a complete cellular makeover. Mitochondria proliferated dramatically, and heat-producing proteins ramped up. A tissue that once stored energy had become a tissue that burns its own fuel. The team called these cells beige fat. And that wasn't all. The team implanted this beige fat around tumors in mice, pitting the tumor against the beige fat. 3 weeks later, the results were dramatic. A rapidly growing tumor had shrunk to less than half its size. The beige fat was drawing in glucose at a tremendous rate and burning it off. With its fuel supply depleted, the tumor could no longer grow. The tumors were unmistakably starving. Experiments using human-derived tissue showed the same result. Above all, what makes this approach beautiful is how natural it is. We take a small amount of the patient's own fat, switch its role, and return it to the body. The team calls this strategy living cell therapy. Now scientists are working to turn it into a real therapy. Of course, we know how this goes. Every time a study like this appears, people feel a flicker of hope, only for it to fade quietly a few years later. Will it work this time? Or will it just fade away again? That skepticism is only natural. We've seen so many attempts fail. But we also know this. Even when experiments collapse, papers are forgotten, and lifelong researchers pass on, the path they forged does not vanish. And here, at the end of that path, are people searching for a new answer. One day, we will starve cancer to death, so long as they don't give up, and so long as we don't give up on them.